Hello everyone. Welcome to another episode of Deep Dive Knowledge. Hello. I would like to learn more about the emerging trends in machine learning for computational fluid dynamics. Can you tell me about the synergies between machine learning and CFD? And the potential benefits and challenges in combining these fields?
Certainly. The intersection of machine learning, ML, and computational fluid dynamics, CFD, has immense potential and is a rapidly growing discipline. In the report, we have discussed the synergies between ML and CFD, as well as the benefits and challenges associated with combining these fields. One of the established techniques where ML has shown significant impact is in the development of reduced order models, ROMs. ROMs are simplified models that capture the essential dynamics of complex flows by identifying patterns and dominant structures. ML algorithms can be used to construct ROMs with simpler dynamics, making predictions of the complete system with lower computational costs. This allows for faster simulations and analysis of fluid dynamics phenomena. Another benefit of combining ML and CFD is in improving the accuracy of simulations. ML algorithms can be trained on high-fidelity CFD data to learn complex relationships between input parameters and desired outputs. These trained ML models can then be used to enhance or correct CFD simulations, providing more accurate results. However, there are also challenges that need to be addressed when combining ML and CFD. One of the challenges is the cost of training ML models. ML models are generally expensive to train, both in terms of the learning algorithm itself and the cost of generating the training data. The training data for ML models in CFD are typically generated using high-fidelity simulations, which can be time-consuming and computationally expensive. Another challenge is the generalization of ML models. ML models are trained on specific datasets, and their performance on unseen data can vary. Ensuring that ML models can generalize well and make reliable predictions for a wide range of fluid dynamics scenarios is an ongoing challenge. Furthermore, it is important to note that ML is not meant to replace classical numerical algorithms in CFD. Instead, the goal is to design new algorithms and frameworks that allow ML and traditional methods to work together synergistically. This requires careful integration of ML models into existing CFD workflows and the development of hybrid approaches that leverage the strengths of both ML and traditional methods. In summary, the synergies between ML and CFD offer promising opportunities for advancing the field. ML can improve the efficiency and accuracy of simulations, but there are challenges related to training costs, generalization of models, and integration into existing workflows that need to be addressed. A balanced perspective of cautious optimism is important when considering the potential benefits and challenges of combining ML and CFD.
Thank you for the insightful explanation. It's fascinating how machine learning can enhance computational fluid dynamics by constructing reduced order models and improving simulation accuracy. I'm interested in learning more about the specific applications of ML in CFD. Could you discuss some of the emerging applications mentioned in the report, such as turbulence modeling, flow control, and non-intrusive sensing?
Certainly. The emerging applications of machine learning in computational fluid dynamics, CFD, have shown great promise in various areas, including turbulence modeling, flow control, and non-intrusive sensing. In the field of turbulence modeling, machine learning techniques are being used to improve the accuracy and efficiency of turbulence models. Turbulent flows are highly complex and difficult to model accurately. Traditional turbulence models rely on empirical relationships and assumptions that may not capture all the intricate features of the flow. Machine learning algorithms, on the other hand, can analyze large amounts of data and learn patterns and structures in the flow without relying on predefined assumptions. This allows for the development of more accurate and robust turbulence models. Flow control is another area where machine learning is making significant contributions. Flow control techniques aim to manipulate the flow behavior to achieve desired outcomes, such as reducing drag, enhancing mixing, or controlling separation. Machine learning algorithms can learn the complex relationships between flow parameters and control inputs from large datasets, enabling the development of more effective flow control strategies. For example, deep reinforcement learning has been applied to turbulent channel flows to optimize control actions and achieve drag reduction. Non-intrusive sensing is an emerging application of machine learning in CFD that focuses on extracting flow information from external measurements or sensor data without requiring direct access to the flow field. Traditional flow sensing methods often involve intrusive probes or sensors placed within the flow, which can disturb the flow and introduce measurement errors. Machine learning algorithms can be trained to learn the mapping between the external measurements and the flow field, allowing for non-intrusive and accurate flow sensing. This approach has the potential to revolutionize flow diagnostics and monitoring in various applications. Overall, the emerging applications of machine learning in computational fluid dynamics, such as turbulence modeling, flow control, and non-intrusive sensing, offer exciting opportunities to improve the accuracy, efficiency, and understanding of complex fluid flows. These applications have the potential to advance various fields, including aerospace, automotive, energy, and environmental engineering.
Thank you for explaining the emerging applications of machine learning in CFD. It's impressive to see how ML can enhance turbulence modeling, flow control, and non-intrusive sensing. These applications have the potential to improve various industries. In terms of the future, what areas of ML and CFD integration are currently under development and may produce important benefits in the coming years?
According to the report, there are several areas of integration between machine learning, ML, and computational fluid dynamics, CFD, that are currently under development and have the potential to produce significant benefits in the future. These emerging areas include 1. Reduced order modeling, ROM. ML techniques are being used to develop ROMs, which are simplified models that capture the essential dynamics of complex flows. By identifying patterns and dominant structures in the flow, ML can construct models with simpler dynamics than the original physical system. These ROMs can then be used to make predictions of the complete system with lower computational cost. 3. 5. 22. 2. Data-driven turbulence modeling. Traditional turbulence models used in CFD, such as Reynolds-averaged Navier-Stokes, RANS, and large eddy simulation, LESS, have limitations in accurately capturing complex turbulent flows. ML techniques are being explored to develop data-driven turbulence models that can improve the predictive capabilities of CFD simulations. These models can learn from large amounts of flow data to better capture the underlying physics of turbulence. 5. 3. Flow control and optimization. ML algorithms are being utilized to optimize fluid flows and design efficient control strategies. By learning from data, ML can identify optimal control parameters or design configurations that enhance the performance of fluid systems, such as reducing drag, improving mixing, or enhancing heat transfer. This can lead to more efficient and optimized designs in various engineering applications. 5. 4. Uncertainty quantification. ML techniques can assist in quantifying and managing uncertainties in CFD simulations. Uncertainties arise from various sources, such as model inadequacy, input uncertainties, and numerical errors. ML can help in developing surrogate models or learning the relationships between uncertain inputs and outputs, enabling more accurate and efficient uncertainty quantification in CFD simulations. 5. It is important to note that these areas are still under development and require further research and validation. However, they hold great promise in advancing the field of computational fluid dynamics and improving the accuracy and efficiency of simulations.
Thank you for providing insights into the areas of ML and CFD integration that are currently under development. The applications you mentioned, such as reduced order modeling, data-driven turbulence modeling, flow control and optimization, and uncertainty quantification, all have the potential to significantly impact the field of computational fluid dynamics. It's exciting to see these advancements taking shape and the potential benefits they can bring. Moving forward, what are the key challenges or limitations that researchers should be aware of when integrating machine learning and computational fluid dynamics?
The report identifies several challenges and limitations that researchers should be aware of when integrating machine learning, ML, and computational fluid dynamics, CFD. One key challenge is the development of accurate reduced order models, ROMs. While ML approaches have shown promise in constructing ROMs with simpler dynamics, accurately capturing the essential ingredients of the original physical system can be challenging. The report emphasizes that even the most complex flows exhibit certain patterns and dominant structures that can be used to construct ROMs. However, it is important for researchers to carefully assess the limitations of these models and ensure that they are able to make reliable predictions. Another challenge is the integration of physics into ML models. The report highlights that incorporating physics into ML models is an area of intense active research. Currently, there are fundamental open questions in ML regarding whether an ML model trained with infinite data from high-fidelity Navier-Stokes simulations will converge to the simulation itself or to the Navier-Stokes equations. This indicates that there is still work to be done in developing ML models that effectively incorporate the governing physical principles of fluid dynamics. Additionally, it is important for researchers to consider the limitations of training data when using ML in CFD. ML models heavily rely on training data to make predictions. Insufficient or biased training data can lead to inaccurate or unreliable predictions. Therefore, researchers must ensure that the training data used to train ML models in CFD is representative of the real-world scenarios they aim to simulate. Finally, the report emphasizes the need for cautious optimism in the integration of ML and CFD. While there are opportunities and benefits in this emerging field, it is crucial to maintain a balanced perspective and consider the potential limitations and challenges that may arise. This calls for thorough validation and verification of ML-based CFD models, as well as continuous improvement and refinement of these models based on feedback from domain experts. In summary, researchers should be aware of challenges related to developing accurate ROMs, incorporating physics into ML models, ensuring representative training data, and maintaining a balanced perspective of cautious optimism when integrating ML and CFD.
Thank you for outlining the key challenges and limitations researchers should be aware of when integrating machine learning and computational fluid dynamics. It's important to carefully consider the accuracy of reduced order models, the incorporation of physics into ML models, the quality of training data, and the need for cautious optimism in this evolving field. By addressing these challenges, researchers can ensure the reliability and effectiveness of ML in enhancing computational fluid dynamics. In conclusion, the integration of machine learning and computational fluid dynamics holds great potential for advancing our understanding and capabilities in fluid dynamics simulations. However, it is crucial to approach this integration with a comprehensive understanding of the challenges and limitations involved. Through careful research, validation, and refinement, we can harness the power of machine learning to unlock new possibilities in computational fluid dynamics.